Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome back in lecture number 11. Student, basically we start equivalent frame method and we did some example on equivalent frame method. This lecture is basically continuation of that lecture series. Student, basically whenever we are designing a flat system or flat plate system, in that kind of slab system, basically the major problem is the shear, punching shear or beam shear. Okay, so this is one of the greatest problem which we basically occurred, and it will control the thickness of the slab in such cases. So punching shear is maximum, basically almost it controls the thickness and it is the governing criteria, while we also check beam shear deflection as well, but the most, you can say, the critical case is the punching shear. Now there are two cases. Basically we will cover the shear strength of a flat slab system in two sections. In one section we basically covered the shear, but we don't consider the movement transfer, while in other part, that is the part B, lecture number 13. Okay, I will cover this in lecture number 13 inshallah, but it will be a lecture number 12, but I will cover this in lecture number 13. In lecture number 12 we covered the numerical portion of this lecture. Okay, and in lecture number 13 we will start the movement transfer. Okay, now in this lecture, basically this is the part, you can say this is the part of direct design method, which I already explained and uploaded to my channel. If you go to my YouTube channel and search this channel, okay, the direct design method, a complete explanation basically I did here, and you must watch lecture number 11 and lecture number 10. This lecture basically covered the complete design of punching shear. What is punching shear? What is beam shear? How to cope with a shear when you facing such kind of problem in a flat slab system. Almost we face this kind of problem in flat slab system. Thus the beam slab supported system, although we check for that for punching shear and beam shear, but in that case it is not a governing criteria. It always occurs and it always exists, and we do checks in the case of a flat slab system. So it is very critical in the case of a flat slab system, and you must watch these two lectures, because this lecture is the part of these two lectures. Okay, so because here so many things I will not explain, and because I already explained, if you go to those lectures and you watch, you see this lecture I thoroughly explained this, okay, this whole lecture, and what is punching shear, how to calculate the critical section or the critical parameter, and how to calculate the tributary area, okay, and similarly for edge column and similarly for corner column, and what are the governing equations for punching shear. I already explained these, okay, and similarly what are the different options when punching shear governs. Okay, so we have integral beam, we have bent up bar, shear heads, shear studs. These are the different arrangement which we can provide to control a shear in a flat slab system. So I thoroughly explained these two options. In today option, basically in today lecture, basically we cover some other ACI criteria which may not be covered on those lectures. So I will explain some criteria regarding to these two, and we will cover this shear heads and shear studs. Okay, basically shear studs, okay, because we don't cover yet this the design of shear studs. So you will understand what is shear studs and what are the criteria, okay, and some examples on it. Similarly, we thoroughly explain what is column capital and what is drop panels, and I have covered these examples, so please go to that channel and watch these two lectures. Okay, so next we start this lecture, but before the starting of this lecture, let me share a video with you people so that you gain some knowledge about shear studs.
You're on a mission to create slim floors and smooth ceilings. Mission impossible? Not with PSB. Reduce the total slab thickness. Design a lower building or more floors. Use it in foundations to reduce excavation work. Install easily by a team of one. In extreme situations, go for the all-new PSB Plus for even more resistance. Wider spans, thinner structures, and lower CO2 footprint. And remember, Payco backs you up by doing the design. High resistance punching shear, slim floors, and smooth ceilings. Easy to design, easy to build with PSB and PSB Plus. For more information, see payco.com/.
So you see the advantages of such kind of shear studs. These are basically shear studs, okay? These are shear studs. You see the shear reinforcement as well. And shear studs, let me share you with some pictures right here. You see these are the shear head reinforcement, and these are the bent up bars, okay, which we basically provide. These are, and let me share another video which is also very you see here the girders which they are placed, okay, these beams you can see which they place at the location of the interior column, because in the location of the interior column the punching shear is dominant, okay. This is very important, and the advantage, as you see in the video, that it will reduce your slab thickness as well as the slab thickness of your footing, okay. It will reduce the excavation work, as well as it by using such kind of reinforcement you can increase your span length. This is also, you can decrease the weight of your structure. So if you are decreasing the weight of your structure, this means you are make economical your footing design, okay. And similarly you can increase the height of the building. So there are so many advantages. If you don't provide such kind of reinforcement, remember, it will result very larger concrete thickness of the slab, both in slab and as well as in footing. So this is the beauty and this is the advantage of such kind of reinforcement. And as a designer, you must be able to design such kind of reinforcement. Let me share you with another document which is very important for you people to understand. You see this Silk luxury apartment location. This is a new construction which is in progress, okay, on Ring Road, Peshawar. And you see this is designed by Professor Dr. Kaisar Ali, okay. And the beauty of this design there, you will see here that they are basically providing these interior columns. You see here there are enormous shear loading on these interior loads, enormous axial force coming to these columns, because it is around about 13-story plaza. So there is a very heavy loading over these interior columns when you are going to design the footing for such columns, and punching shear will govern. And you see the reinforcement, how heavy reinforcement they are going to provide for such kind of plaza. You see here the integral beam. This is the shear reinforcement which they basically provide to control that heavy loading from the top of the structure. If you don't provide such kind of reinforcement, such kind of integral beams or shear reinforcement, it will increase the slab thickness. For example, if you see thickness of this mat, this is basically the integral beam which they designed, and I thoroughly explained this in that lecture, in those videos. So please go there and watch those videos. And you see that the depth of this integral beam is around about 28 inches. Okay, so this is very important that you may be able to design such kind of. And if, for example, if you are a site engineer, basically so many students asking me about this, the design of this integral beam, they don't know about this this kind of arrangement. This is basically, if you have knowledge about this kind of integral beam, so you must understand why we provide this kind of reinforcement. Okay, and what are the design principles and what are the AC criteria regarding this kind of reinforcement. Now let me share you the thickness of this mat, which is around about 48 inches. You see here, if you don't provide this integral beam, remember this thickness may go to, you can say, 2 times, 3 times of this thickness. So by using this kind of beam which control the punching shear, so it will decrease the thickness of your mat. And as you see in the video that they explain that it will reduce the thickness of your structure. So this is the beauty and this is the advantage of such kind of reinforcement. You must be able to design such kind of reinforcement. Okay, so let's start. You already know we have a beam slab supported system, we have a flat when we don't provide such kind of column capital or drop panel, so this is called flat system. Okay, and this is, and you see the pictures, think about this span. Okay, this is the beauty. Okay, this is the beauty if you are providing column capital, drop panels, shear reinforcement. You see how much far away the columns are. Okay, so this is the beauty. Now you see here the slab fails in punching shear. Okay, and this is the example that this kind of pyramid shape is basically formed when punching shear occurs. While in beam shear, you see there will be a one-dimensional crack. Okay, and this truncated shape, you can see the column you see here. There are so many reports which if you Google it, and you will find so many casualties occurs in such kind of failures. So this is the most dangerous failure. Remember, this is the most dangerous failure. And I was reading in a book, basically he says that there is a forgiveness. There is amount of forgiveness if you make any mistake while calculating the reinforcement for flexure. Okay, because in flexure there is a huge ductility in a structure and there is moment redistribution occurs, and the structure is you can say the structure could not fail abruptly. They give you some kind of prior warning, but in shear there is no forgiveness. If you make any mistakes in calculating of shear, there will be no forgiveness, and such kind of failures is abruptly occurred, giving no prior warning, and it will become the cause of many losses, both living and non-living things. Okay, so great financial losses and so many things. Okay, so two types of shear failure basically occurred: beam shear failure, which is called one-way shear, and two-way shear, which is called punching shear. You see in punching shear, this kind of cracks basically occur. The columns go in upward direction, the slab going in downward direction, and this kind of truncated shape of the column you will see here. Now, when such kind of failure occurs, and we analyze such kind of failure by using Truss Model. So what does it we do in Truss Model? Basically, in Truss Model you see here that these are the bars. Okay, these are the steel bars. Now you see here basically when such kind of failure occurs, like such cracks occurs, so here basically a strut is developed. Okay, a strut basically develop here. This portion basically move in downward direction, this portion basically move in upward direction. Now the most important thing that this strut has two parts, which one is the vertical part and the other one is the horizontal part. Okay, the horizontal part basically it causes change in the, you already know that in the column portion we have a negative movement in top region and positive movement in the in compression, okay, in the downward region. So here we have a torque and tension, and here we have compression. So this kind of force, which is the horizontal component of that strut, is basically bring changes in these tension force and compression force. Okay, so this is you can see adding some extra force, and such kind of failures occurred the complete failure of the slab. So this is the Truss Model, and here you see such failure occurs suddenly with little or no warning. So this is very important, clear? And similarly, when such kind of failure occurs, remember, whenever basically a slab fails in flexure, so there is you can say a moment distribution. For example, you have a beam, okay, and you have a support right here, you have a support right here, similarly support right here, and let's say the beam fell at the mid, and you can say here is the plastic hinge occurs. So there is in flexure there is moment redistribution, mean that this moment capacity now distributed to this point, okay, this point, and similarly to this point, and now they are taking the loading which present here. Now these portions taking the loading, but in shear such kind of behavior is not present. Shear didn't distribute, and it causing the overloading of the other force columns, and as overloading of those columns, it will causes the failure of the slab. So this is the total mechanism, this is the whole mechanism of the failure of the shear. You see here that in flexure the two-way slab possesses great ductility if it fails in flexure, but a little ductility if it fails in shear. Okay, now the next thing is that when we calculating basically, or we are going to design for a shear, so we have interior column, we have circular column, we have irregular column, we have edge column, and how to calculate column critical parameters. So I already explained these criteria in those lectures, so go and watch. Okay, basically you must remember this is the critical parameter or critical section, which is in the case of punching shear, it occurs from the face of the column at a distance of d/2 to both sides. And if it is a beam shear, so it will occur at a distance of d distance in one direction. Okay, now these are the ACA criteria basically, which explains that whenever you are going to design in the case of a drop panel or a punching shear, you have to consider some critical sections. In each critical section you have to satisfy the criteria, that is your pi VC should be greater than or equal to your VU. Okay, remember most of the time we don't go for the shear reinforcement. Okay, there are some reasons I will explain later, but we trying to control the shear by the thickness of the slab. But if thickness going to be more, so then we are compelled to use the shear reinforcement. So in case of a drop panel, ACA criteria says, code section says that you have to check for two critical section. The one is the inner critical section, you see here, this one, which is a distance of d/2 from both the faces of the column, and the one section is from the face of the column column drop panel, sorry, and the section will be this one, and it will be from the face of the capital at a distance of d/2. Okay, so we have outer section and we have inner section, and we have to check the capacity at both sections. Okay, so you will see inshallah in example, you will see that we will check for the both sections. This is very important that we have openings, okay, in slab system, and we are compelled in so many cases that we will provide openings, okay, to the staircase, to the lift shaft, and similarly they are for ventilation purposes. And so many cases there are that architect basically compelled us, they provide such kind of openings in a slab system. So if such kind of openings present in a slab system, what are the criteria of ACA code? So ACA code criteria says that if this opening comes under this critical parameter, for example, the code says that when openings are located at less than 10 times the slab thickness, okay, you measure the distance of the opening from the face of the column, and if this distance is less than 10 times the thickness of the slab, then you have to ignore this part. You see, this part is basically ineffective then. So find out the B0 and subtract this distance. Similarly, for example, in this case, similarly for a left shaft or any other case. Okay, and remember there are so many cases. For example, let me share that document. Okay, you see here we have to provide stair and elevator shafts. Okay, and for ventilating purposes, okay, we have to provide these openings. Similarly, relatively small openings usually are not detrimental in beam supported slabs. In beam supported slabs, this is not dangerous, you can say. You don't worry about this. But as a general rule, the equivalent of the interrupted reinforcement should be added. This is very important. Okay, that for example, as you see here, that when we are going to provide a hole, okay, so the bars which we are basically providing, let's say in column strip, sorry, so they are interrupted right here. So this means that the interrupted steel should be provided. You should not discontinue. You should not ignore that amount of steel. Okay, you have to provide that reinforcement along the sides of this hole. This is very important. Okay, and you have to properly anchor these bars right here. And similarly, SA code says that you have to provide the diagonal bars. Okay, this is very important, and you have to provide these diagonal bars. Okay, there are certain criteria that how to provide. I will share you inshallah in my coming lecture that how to provide these diagonal bars. Okay, and these are the SA criteria. Okay, and similarly they will explain additional diagonal bars should be included at the corner of the okay, and they are best located. Now the places basically where you have to provide the holes. Okay, for example, in a column strip area, which is, you can see, which is the most dangerous area. Okay, and remember, architects are always trying to provide such kind of holes near the column face. Okay, and near the column face you already know that there is enormous amount of negative movement. So basically that why the location near the column face, it is the most dangerous location. The best location is the middle column strip area, where you can provide those kind of holes or openings, but near the column it is very dangerous. Okay, so you can go to McGregor and you can McGregor book or Nielsen book and you can read this paragraphs. Okay, the next thing is this is very important case. Okay, for example, in the case of H column, when you are calculating your critical parameter, you already see that the H column, in the case of H column, there is some cantilever slab. Okay, some cantilever slab in some cantilever slab present. Okay, so ACA code says that if a cantilever slab, let's say, if present along the edge column or along the corner column, so whether you have to go forward from the face of the column or not, or this means that whether you have to consider this RS distance or WV distance or not. This is the question. You see, AC code says that if this A and B distance, if it is more than, there are two criteria. If it is more than 4H, or if it is more than twice the development length, 2LD. Okay, so SA code allow you to calculate, or you can add this RS and VW to your B naught. Okay, this means that your B naught will be start from here, and this one will be your B naught. If this is less than RS or VW distance is less than this 4 times of HR 2LD, so you don't consider this RS and WV, and in that case your B naught will start from V, okay, and stop or ends at S. As usual we do it. Okay, so this is important. Similarly, you see here, and similarly this was the case sometime you have to see this kind of situation that the B, you see here, critical parameter if A exceeds, A fulfill these two criteria but B doesn't. So in this case what you have to do, you see here, we will consider Now remember, in the case of corner column, this is our beta naught. Okay, this is our beta naught. If the criteria doesn't satisfy, critical parameter of A and B do not exceed the greater of these two. So this one, okay, as usually we calculate the beta naught. But if it is, let's say here it says that if A, this side fulfill these two criteria, but this side doesn't. So your parameter now will start with this one, okay? Now it will be this one. This is very important, okay? And inshallah you will see, we will do this in our example and you will thoroughly understand it, okay? You see, in the case of H column, now this A fulfill the criteria, so in that case our parameter is this one, okay? But here you see the full parameter. So this is how these two criteria basically. For conservative approach, you can just take the parameter as we did here, okay? As in this case, you can, for conservative approach, you can choose the beta naught value as we did in our examples, in this examples, okay? Similarly for this, and similarly that doesn't show it for the corner column, but you can calculate it for the corner column as well. Now next we have, you already know it, okay, that how to calculate the tributary area for a corner column, for an edge column, and for a interior column. It is very important. You have to calculate this critical parameter for each column. You see here, now this one, okay, if the slab continues and it fulfill the criteria, then it will be, we can add this portion as well, okay? So this is very important to understand. Similarly for the corner column. Now how to calculate basically the tributary area? So always we consider from the center to L by 2, from the center to L by 2, and for a corner column this is our tributary area. For an edge column, both side L by 2, L by 2, and to this side it is also L by 2. For similarly for this one. But one of the SCA criteria says that if you have, let's say you have an interior column, so for an interior column from the mid, you will we always basically consider L by 2 to this side and similarly L by 2 to this side as well. But this is the SCA code criteria that you have to increase this side, because in this, if we are analyzing this slab system in this direction, so this is the first interior column and this is the exterior panel. So in the case of exterior panel, we will increase this length by 15%, and you will be familiar with this when we are let's say we draw our shear diagram, okay? So you see that at first support we consider the shear at a distance 1.15, 15% more as shear value right here, okay? So you can go for this, okay, 0.5 times 1.15 for the case of this first interior support. Clear? Now this is the design criteria. We have always tried to that our design shear strength, the capacity in the shear of our slab should be more than the shear force, okay? And we always use this basic equation, Vn equals to Vc plus Vs. V is the shear which is provided by the shear reinforcement if we are using shear reinforcement in our slab. Sometimes we use, sometimes we don't use. And this is the Vc. Here is the reason that in the initial of the lecture that I will say, don't try to use shear reinforcement. Always trying to control the shear by using Vc, okay, Vc. This is the reason, for economical reason, because when you are placing shear reinforcement, it needs labor force. It needs some time, more time. And the placing in such, because you already know the thickness of the slab is 7 inch, 8 inch, 10 inch. So this is very difficult to provide such kind of shear reinforcement in this narrow thickness. So that's why they basically suggest, designers suggest that you have to control the shear by Vc. If let's say that doesn't control, okay, so then you go for the shear reinforcement. These are the basic equation which is used for punching shear, and I thoroughly explained basically in this lecture. So go there and watch those lectures. Now remember, this term is basically, let me add something extra. This beta naught is what? It is the ratio of A divided by B, means that the longer side to the shorter side. If you have a rectangular column, because in the case of a rectangular column you have to use, and we use this equation in our footing as well. So beta is the ratio of this side to this shorter side. If this beta is, let's say, less than 2, so we don't consider this equation because this is not a governing equation. And if it more than 2, then you see that in that case basically this equation will govern. Okay, it will more than 2. Okay, for example, if it is less than 2, so divide this one, and it will, because if it is less than, so this value, this whole value will be lesser than 4, so that's why it doesn't control. But if this value more than 2, so the value, let's say if it is more than 2, so you got value which will be lesser than that one. Okay, and then this value will control. Okay, so this is important, this is very important. Okay, and I will share you in the example. Now this is the graphs from where we can take this kind of equation. Okay, this equation is basically from the first graph. You see here the values right here, these are different from different test results. You see this is the average value. Okay, and then the values are, you see down here. So to cover this, we consider this portion, and this portion is basically covered by this value. Okay, this one. And remember, this thing is very important, that in the case of a rectangular column, a highly rectangular column, there will be enormous shear at the corners and there will be lesser amount of shear at the middle portion. So that's why we are always considering an average value, that is FC prime beta naught into D. Similarly, this equation is for equation 24. This part is basically covered by equation 24, and you see the drop in values. So to cover this value, we basically consider this part, and this is covered under this equation, this part. Okay, this variation is covered by this part. And when we consider this, when your beta naught to D ratio, when it changes, you see here it increases. So if this ratio increases, so you see the abrupt change in the strength of the concrete, shear strength of the concrete. Okay, so that's why basically we consider this alpha S, and alpha S is 20 for the greater than 20, and there are different values. I think so for corner column it is 20, 30 for edge column, and 40 for interior column. Now for one beam shear, you already know we use this equation, clear? And these are the net summary. You can say that for a beam shear, you see here we consider the critical section at a distance D from the face of the support, and this is the this is the area which we will consider for a beam shear, to check the beam shear. Okay, and this is the whole in the case of interior column, this will be the whole tributary area. Okay, which will be multiplied with the force, that is QU, and we got the VU value basically. And this interior area which is bounded by this critical section will be subtracted. Okay, and we got the value of that is VU. Okay? And we have to use the 3 equation for the punching shear, and we use this equation for the beam shear. Okay? Now we have an example. So read the example, and first of all you have to calculate the average. So the slab thickness in this equation, in this question, is 6 inches. So 6 inches minus 0 point, this is the concrete cover, and this is the bar diameter. How to calculate the D average? So you must know that how to calculate the D average. Remember, here you see the bars are placing in the top portion for negative reinforcement, okay, for negative movement. And this bar you see here, from the top surface of that top bar, this is our clear cover. Then you have to subtract this die of this bar, okay, you got the D average, as we did for the two-way slab design, okay. And what we have next, we have this kind of slab system, 18 by 18 in both direction, and we have to check this column for punching shear as well as for beam shear. So we need to calculate the tributary area for both beam shear and for both punching shear. Clear? Now, what will be the tributary area for the punching shear? So you see this 9 plus 9, because we have to consider this side, okay, this side, and we have to consider this side. So from the center of the column, it is 9 feet, and from this side 9 feet and 9 feet. So 18 by 18 feet will be the tributary area for punching shear, subtracting the critical section area. Okay, remember we have to find out that area, and we have to subtract this area. Now you see this line is basically representing the critical section at a distance D, remember, for beam shear. And similarly this critical section at a distance D from the face of the column, and it is for beam shear. So you see this AA section is, the length of the AA section is more than BB, so this AA will be the governing section for beam shear, okay, and we will use this AA. Clear? So find out the QU value. You already know thickness of the slab times the superimposed dead load times the live load, okay. And check for one-way shear. So for one-way shear, you see here we have section AA and BB, but section AA govern because this is larger. Computed section AA, so you have to find out VU. So how to find out VU? You have to multiply your QU with the beam shear area, and in this case it will be for beam shear this area, remember this area. So find out this area. How to find out this area? This side times this distance. How to find out this distance? So you see here this distance is 8 feet, 8.10 feet. It is from the center, subtract this D, subtract this side, that is 12 inch, okay. So 12 divided by 2, you got the 6 inch plus 4.76, I think so, divided by 12, subtracted from 9, you got this 8.10 feet. Now, and you see now this is the shear force, okay, and check out the beam shear strength and the strength of the shear of the concrete of the slab or concrete. So you see here they're using the beam shear equation, and you got 84, which is far away from VU. So our design, our beam shear check is okay. Now we have to proceed for punching shear. So for punching shear we have 18 by 18 feet tributary area, and we have to find out this area which is bounded by these critical section. So we find out the one side of this critical parameter and the other side of critical parameter. Okay, you see one side is 16.75, the other side 30.75. So multiply it, you got the total interior area. So you just need to subtract this area 16.75 divided by multiply by 30.75 from this whole area. Okay, so this is the way, okay, they did it. We got the VU is 65.4 kip, and now we have to use those three equations. We have to calculate beta naught. Okay, beta naught is the length of the critical section, okay, this section, this one. So how to find out 16.75 times 2, because we have two sides, and 30.75 with 2 because we have two sides. So our beta naught, B naught will be 95 inch. Use the basic punching shear equation, which is this one. Now you see we have to find out beta. So it is more than 2 right now. So that why as it more than 2, so this will be our governing equation. If it is less than 2, so we ignore this equation. Okay, remember this is basically we did to reduce our calculation. Okay, And here you see 95. So this is the governing equation and we have to ignore this one. So we have to check the other equation as well. Alpha S, here as it is an interior column, so we will use 40, and you have to plug all the value, you got this one. So this is not a governing equation, so ignore it and consider this value. So 95 is more than the VU. Okay, 95 is more than the VU, that is remember you have to multiply it with 0.75 to reduce it. 71.3 is the shear strength of our concrete section, which is more than 65, which is our VU. So our design is safe. The thickness of the slab section, that is 6 inch, is now in shear basically it's satisfied. This is important. For example, this is very important question, that let's say if this criteria doesn't satisfy. Okay, this criteria doesn't satisfy. So what we have to do next? Remember, if phi VC is let's say it is less than VU. So in this case, what we have to do? I already explained this here. Okay, we have to provide different arrangement, and those arrangements are here. But here you see the graphical representations of different techniques. Remember, if such kind of condition, let's say, prevail, then we have different ways to cope with such problems. Okay, the ways are, you have to provide drop panel, you have to provide column capital, you have to provide shear head reinforcement, you have to provide shear studs, okay, bent up bar, shear reinforcement, integral beams. Okay, these are the different options, and this is the graphical representation. Clear? Now, remember, if you are providing your integral beam, I already explained the design, the criteria of integral beam in those lectures, but this is some extra sections of ACA code. Okay, now you see, if you are providing the shear reinforcement, as you see here in this diagram, that let me show you that diagram, because integral beam have certain ACI sections. You see here these bars. Okay, each bar should be these horizontal bars should be, you can say, should be confined by these corners. Okay, remember, this is the ACA code criteria, and as you see here, each bar is basically confined by the stirrup. Okay, this is important. And remember, this distance should be less than or equal to 2D. This distance should be greater than or equal to 12 dB. Okay, and the hook specifications you see here, 45 degree maximum, 6 dB, and similarly this is also code specifications. So these are some extra, okay, that I have to add with you people. This is the design of ACI criteria for the stirrup integral beam. Okay, that the first stirrup should be provided at a distance of less than d by 2. Okay, and this is our exterior critical section. Okay, and from that exterior critical section, outside critical section, the last stirrup should be at a distance of d by 2. Clear? And these are some extra, that stirrups are allowed in slabs with effective depth d that exceeds the larger of 6 inch. Remember, you have to provide shear reinforcement in your concrete slab when the thickness of the effective depth, remember, it should more than 6 inch or 16 times the stirrup diameter. You have to check this. Okay, and the next, this is the ACA code, some experimental result both by ACA and ACE, that it is stated that the measured shear strength of slab with stirrup as shear reinforcement exceeded the shear strength of the concrete section and also exceeded from the stirrup alone. However, the report goes on to say that in most cases the measured shear strength was, what does it mean? It means that in most cases, as you see, that we calculate our Vn. Vn was what? Vn is the combination of Vc plus Vs. Okay, you already know it. Now the value which we calculate already, this satisfied basically the condition, but when we did experimental work on it, and you can say experimental results, basically it shows that the calculated are the experimental values which we obtained for Vn, it will be less than the Vu. So this is, you can say, a warning sign. This is the ACI report. So it basically suggests, here it says that the thickness of the slab should be such that you have to fulfill this 6 inch or 16 times. Okay, or in other report, which is 1962 report, it says that it must be greater than or equals to 10 inches. Okay, because if the thickness of the slab is less, the effectiveness of the shear reinforcement will be less. Okay, and next is the structure steel shear heads. Now this is another arrangement, and I already explained this here. This is the shear head reinforcement, and here we basically place ice section girders, channel girders, okay, beams, and they control it. It will also increase the shear strength of the section, and it will also increase the flexure capacity in bending as well. Okay, and there are different ACA criteria sections, okay, which explain how to place these and what are the recommendations for such kind of reinforcement. I think so it is explained in ACA code chapter 11. You can go there, and I think so in some part in lecture chapter 22. So you go there and watch and read those sections. Okay, although there are some limitations, some advantages of steel shear head reinforcement, and remember it is mostly adopted for the steel columns. Okay, and the next one is the headed shear studs. Okay, this is the important one. Okay, and we will do some numerical on it. Okay, now this is important. You see here they are placing the shear studs in 1, 2, 3 rows in this direction, 3 rows in this direction. Okay, now such kind of arrangement will be provided. Okay, so this is the, remember there are some ACA criteria that this stud head is very important, and due to this head, basically the effectiveness of the shear stud is more as compared to stirrups. Why? Because this kind of head producing a confinement action over the slab. Okay, and due to this head, basically this head should be enough. It is around about 3.2 times of the shop diameter, and because it should be more, because this part basically is responsible for developing the yield strength in this bar, in this steel. Okay, so there are ACA criteria. Okay, and you see here it will be 3.2. this head diameter should be 3.2 of the diameter of that, okay, of that portion. And this is the arrangement you see here. Sometime if, let's say, the shear punching shear is maximum, so we will provide some radial, okay, radial shear studs. Remember this horizontal portion you see here, this is called rail. Okay, so combinedly it is said stud rails, but this portion is we call it rails. Okay, and the studs are basically, these are shaft welded. Okay, these are basically shaft welded provided, and we have to check it both in interior critical section as well as at the outer section. Clear? And these are the ACA criteria you see here. The horizontal distance should be less than in two adjacent rows. It should be less than or equal to 2D, and similarly you will see the specification which will be used for this S distance, which is spacing. Okay, and this is S. Okay, and remember, yes, we will explain it in later. Okay, now here you see they generally shaft welded. Okay, and you see here tests suggest that the area of the bearing surface of the head should be at least 10 times the area of the vertical rod to enable the yield strength. This is, I already shared with you that, remember, the head is very effective, okay, to produce the yield strength in this shaft. Now its area should be 10 times, okay, to the area of this vertical rod, remember. And if you are interested, go and find this research paper which is relevant to the design of shear studs. Adding additional stud rails radiating, I already explained. You have to provide such as you see here, not in this video but in previous video which I will already share, that the Steelers is providing in the radial direction as well. Okay, now shear reinforcement for two-way slabs. These are the stud strength, that is FYT will be 51 KSI, and these are the diameters, various diameters of the stud. Now how to calculate the effective depth, okay, or the depth D average in case of stud reinforcement? So you have to subtract these three things from the overall thickness, that is 7.5 inch. So the top clear cover and as well as the bottom clear cover and one top reinforcement, okay, one top reinforcement, I have the one top reinforcement, one half the diameter of the tension flexure reinforcement. Either it is provided in the top portion or whether it is provided in the bottom, but as the studs are providing in the column region, so that why we have always the flexure reinforcement in the top portion. So you have to subtract half, okay. So this is the way that how we calculate the average, okay. Now inner critical section, I already explained it. We have inner critical section and outer critical section, and this type of discussion is very important. ACI code section, it suggests that you have to use VC, which is the design shear strength of the concrete, shear strength, okay, which will be used 2 lambda FC prime, not 4 lambda FC prime. This is very important question. ACI basically reduce the shear strength of the concrete up to 50%. Why this reduction was? This is very important question. The reduction from 4 lambda to 2 lambda on the inner critical section is based on the test results. Okay, this is very important. Let me explain it. In the punching shear, as you already see that at this inner critical section, the punching shear strength of the concrete is 4 lambda. Okay, we already know it, 4 lambda FC prime, beta naught into D. But ACI code says that at the interior critical section you have to drop this value to 50% drop, and you have to use this 2 lambda FC prime. This reduction is due to the test results, that if you are providing shear reinforcement, you have to consider this one will be the shear strength now, not this one 4 lambda. If you are providing shear reinforcement, remember, if you don't provide shear reinforcement, then go for 4 lambda. But if you are providing shear reinforcement, then you have to consider the punching shear strength at this section will be 2 lambda. It is due to the test result which basically shows that the value which we basically experimentally calculated, as I already explained, that Vn is the sum of Vc plus Vs. Okay, Vs. Now the value or the strength which is predicted from this equation, okay, is almost higher as from the test results. So that why ACI code says that you have to reduce this shear strength from 4 lambda to 2 lambda, or mean if you calculated Vc from 4 lambda, then you have to divide it by 2. And now this one will be now your final strength in concrete, and you have to compare that value with the VU. Okay, you have to compare that value with the VU. Okay, so this is very important. This is very, very important. Vc should be taken to this value, not 4 lambda. Although in punching shear we consider it as 4 lambda, but remember 2 lambda will be used when shear reinforcement is used. Without shear reinforcement, remember, we don't consider this 2 lambda, we consider 4 lambda. This is very important. Okay. The other thing is the cracks. We have potential cracks and we have critical cracks. And remember, you see here the solid one is the critical crack, while the dotted one is the potential shear crack. And remember, SA code says that these stirrups should be provided that it must cross this potential shear crack. Remember, this is very important. This is the SA criteria. The other thing is that here it basically explains the spacing of the studs. Okay, it suggests that the stirrups legs that surround the column shall not exceed d by 2. Okay, and to intercept potential shear failure cracks further from column, okay, this is for shear reinforcement, not for studs. Okay, I will explain for stud as well. The spacing of the studs, basically, as you see here, the spacing of this shear reinforcement, it should be less than d by 2, or it should be calculated from this equation, which is S. Okay, so the minimum value from the minimum value will be selected. Clear? And the next one is the arrangement. I already shared this arrangement. The first stirrup should be placed a distance of d by 2 or less than, okay, less than or equal to d by 2. And remember these bars, okay, the stirrup bars, which is basically provided in the case of integral bars. Remember, this is very important. Let me you see these horizontal bars which is providing in the integral beam. You see this one, this one, this one. The inner to inner distance should fulfill this criteria. It should be less than or equal to 2d. Okay, this is important. And spacing should be less than or equal to d by 2. Now, this is important. This is very important, that your Vn should be greater than 6 times Fc prime under root into beta naught. In case of stirrup type shear reinforcement, Vn shall not mean that this is the same criteria as we are using for shear in the case of beams. That in case of beams, if your VU, I think so, Vs, sorry, if it is more than the 8 feet times Fc prime under root, so in that case we revise the dimensions of beam, because if you go in such case, it will become the cause of the heavy congestions of shear reinforcement. The stirrup spacing will be very close and it causes the congestion problems. So same things right here, that your Vn should be less than 6 times into Fc prime beta naught. Okay, should be less than. If it is more than, then it will causes the congestion problems. Okay. And similarly for stud reinforcement, as we did in the case of shear stirrups, we have to consider Vc equals to this value if you are providing shear reinforcement. If by shear reinforcement by using stirrups, if we are providing shear reinforcement as slab by using studs, then we have to consider Vc equals to 3 lambda Fc prime under root. But these are the recommendations of different designers that don't consider this value, go for this value. Okay. And as in the case of the shear, in the case of the stirrups, we have to consider 6 times Fc prime beta naught into d. But in the case of studs, shear studs, we will take that, we will replace that 6 by 8. Okay, so a higher value. Okay, so this basically suggests the effectiveness of shear stud reinforcement, that shear stud reinforcement is more effective as compared to stirrup reinforcement, because due to their confining action, which is provided by, from the bottom it is provided by the rail, and from the top it is provided by that head. Okay, so it creates a kind of confining actions, and it will as the slab is compressed in the vertical direction, due to that shear strength is increases, and that's why we are, as code suggests, that you go for higher values. Okay, now next is the spacing recommendation for stud reinforcement. Remember, if you calculate your Vn and it comes out to be greater than this value, 6.5 FC prime under root, ACA code suggests that your maximum spacing should not be more than 0.75 times FD. If your Vn value is more than this value, then the maximum spacing will be d by 2. The center to center spacing of the studs, let me share here. Okay, here you see this S in this direction. If the Vn value is less than 6 times FC prime, then go for 0.75 times d. But if it is in the case when Vn greater than 6 times FC prime beta naught, so this S should be d by 2, should be less than d by 2. Okay, and this is the code recommendation portion, this section 11.11.52. okay, and the next is the arrangement. You see here for interior column, for an edge column, I already explained these things. First stud should be placed at a distance of d by 2, less than d by 2, and the center to center place distance. Okay, remember, let's say for example you have this size is 12 inches. If the column size, this side is 12 inch, then you have to place 2 rows, you can say, and because you have to fulfill this criteria. Okay, you can't increase this from 2D. okay, and similarly in case of corner column, same recommendations. Okay, and in the case of corner column, okay, same recommendation. And this is ends of this lecture. In next lecture, inshallah, that is lecture number 12, we covered these examples. Okay, we have 3 to 4 examples inshallah, and we will cover those examples, and you will understand thoroughly this whole theory. Okay, how to fulfill these criteria. Okay, but remember, in this case we don't consider movement. Remember, in the next part, which is this part, okay, and where we will consider the moment transfer, and that will be the most important lecture inshallah. Okay, we will cover it. Thank you for watching. See you in next lecture.